Okay, stats class. For this week, instead of kind of our normal video, I need to write this out by hand. So this is kind of your assignment. You don't have to write everything in here online, but I'll show you the parts that you do need to do. And what we want to talk about is our review of histograms. Histograms become a strong part uh, uh, of statistics, and the histograms generally have this type of shape to it. And so as you see that, we call it the normal curve, sometimes referred to as the bell curve. So bell curve has some interesting properties about it. Number one, it has a bell shape. Uh, Lots in the middle. So you see there's a lot of area in the middle, little at the end, not much on the ends here. Okay. The area underneath is 100% or 1. 100% is the same as 1. So if we looked at all the area underneath this curve, we would say that it is exactly 1. Okay. And that's actually what we refer to as the density curve. Now, I want to be clear about kind of how we talk about a bell curve. Sometimes you hear the idea that teachers curve their tests. Well, if that was really true, what that would mean is that the majority of people would get C's, and then some of the people would get B's and D's, and then very few people would get A's and F's. And that's what truly curving a test means, is that what it means is this: is if everybody on the test got A's, B's, and C's, we would end up stretching that to make sure that so the A's would kind of be A's and B's, the B's would really turn into C's, and the C's would turn into D's and F's. So that's what a bell curve actually means. Whereas if you had a curve that was a CDF, and they decided to bell curve it, everybody in the class got F's, D's, and C's. That means some people still got F's. The D's would probably turn more into like C's, and C's would turn into A's and B's. So when you hear that a teacher maybe curves a test, it probably isn't a true curve. That's what that actually means. Okay. The median and the mean end up being the same. They're right in the middle. Okay. We're not going to write all the stuff that we've covered there in the past. But then we have this interesting thing, which is standard deviation. Standard deviation is what we call sigma, and mean is what we call mu. So just like we have variables x, y, z, when we talk about the variable for mean, we use mu. Mu is the Greek letter for m, and sigma is the Greek letter for standard deviation, or for s, and we use it for standard deviation. Standard deviation measures the spread or variance of the data. So it really measures, how far do we go in either direction before the curve starts to tilt and go the other way. Okay. Some other interesting things about the bell curve is, we like to see that it is, that the mean, the median, mode are right in the center. Sometimes we see it skewed to the right, meaning it tails off a little bit to the right. And in that case, the mean ends up moving to the right. So the median is still here, whereas the mean moves to the right. Whereas if you have a skew to the left, we call it a negative skew. You see it tails off to the left. The median's still in the middle, whereas the mean pushes off to the left of the median. So a lot of times we say that the median is the best representation of the data. The median is what we like the most. The mean, it's okay. You know, you're saying now it looks mean or angry. Maybe not. I don't know. The mode, definitely not the best representation of the data. It's one thing, but yeah. So the median is a great representation. Let's talk about what some of this stuff means. Okay. As we look at the data, what's really interesting here is that 68% of all observations fall within one standard deviation of the mean. Okay, so if you have a normal curve, which means then that the mean, median, mode are all at the same spot, 68% of all observations fall within one standard deviation mean. That means that if we go one standard deviation this way and one standard deviation that way, notice what we have here. We have 34% there and 34% there. That adds up to 68% of the data is within that one spot, one standard deviation from the mean. Here's the other thing that's interesting. 95% of observations fall within two standard deviations of the mean. So if you move two spots away, you can see we would take that 68. If you take that 68%, you add to it 13.6 and 13.6, you come up with 95%. So most all of the data lies within two standard deviations of the mean. And finally, 99.7 observations fall within three standard deviations of the mean. Now, we're not taking time to show how the standard deviation is calculated. It's pretty involved. Most people use a calculator for it, but we're gonna use an example here. So you're gonna do two examples with me, and then you'll do two examples on your own. Okay. So it says the average life expectancy of men is 74 years, with the standard deviation of 7 years. Use the 68, 95, and 95.7 rule to answer the questions. So what I'm going to do is I'm going to draw a bell curve here. All right. And in the middle, I'm going to put that I'm 74 is my mu, and that it's my mean, and that sigma is 7. That means that if I move 7 here, I get to 81. And if I move 7 this way, I get to 67. So that's one standard deviation away from the mean. So it means what is the range of years of lifespan for 68% of men? It would be 67 years to 81 years. That means that 68% of men live to be between 67 and 81 years of age. What is the range of years of lifespan? 95%? Well, that I move two spots away. So I add another 7, I get to 88. And I subtract 7, and I get to 60. So just about all men, 60% or 60 years to 88 years. So all men live to be somewhere between the age of 60 to 88. And finally, what is the range of years of lifespan? 99.7. Well, we go three spots away. And that would bring us to 95 and then 53. So 53 years to 95 years. So it tells us the type of span that is typical for men's lives. Look at this question. What percent of men live longer than 67% or than 67 years? So we are looking at this mark right here, 67, and what percent of men live longer? Well, we're going to add up all of those areas, and we can find those areas right here. 34.1, 34.1, 13.6, and we have 2.15. And that will give us an estimation. I'm going to pause this real quick. Okay, so I turn on my calculator. I'll add those up. 34.1 plus 34.1 plus 13.6 plus 2.15. And it looks like about 83.95%. 83.95%. And then finally, the last question here says, what percent of men live shorter than 88 years? So I'm wondering, this 88 and shorter is going to be back this way. Well, I know that's 34.1, that's 13.6, that's 34.1. This is 13.6, and then this is 2.15. So I'm going to add all those up. 2.15 plus 13.6 plus 34.1 plus 34.1 plus 13.6, and I get to 97.55. 97.55% of men live shorter than 88 years. Okay. Very good. You know what? We're right at 11 and a half minutes. I'm going to stop that video, and then the second example will be on the next one.